In today's lab, we'll be studying magnetic fields. So as most of us know, magnets have a north and a south pole. Magnetic field lines start on the north pole, circulate around the outside of the magnet, and come back in on the south pole. If we place a compass needle, which is just a small magnet, in that magnetic field, then the north part of the compass needle is going to point in the direction of that magnetic field. The magnets that most of us are familiar with are permanent magnets, or magnets that have a permanent magnetic field surrounding them. But the same thing applies to electromagnets, which are magnets or magnetic fields produced by electric current. And in that case, you can actually turn it on or off or vary the magnetic field strength by varying the electric current. One of the simplest electromagnet configurations is the current loop, which is a loop or loops of wire in which current circulates and produces a magnetic field that comes through the center and then wraps back around the outside. If we assign coordinate directions to this coil, where the z component is pointing up through the center of the coil, then the z component of the magnetic field, or Bz, should be equal to n times mu naught divided by 2r times I, where n is the number of turns of wire in this coil, mu naught is the permeability of free space, or the magnetic constant, r is the radius of the coil, and I is the current flowing through this coil. Based on this equation then, if we vary the current I, we should be able to control the z component of magnetic field, Bz, and a plot of Bz versus I should be a linear relationship. Now, doing this on Earth, there will also be a constant magnetic field present, the Earth's magnetic field, but this won't affect the slope in this equation, so we can kind of ignore that. So in this lab, we have two parts. In the first part, we'll be mapping the magnetic field of a permanent bar magnet, and in the second part, we'll be measuring the magnetic field strength of a current loop. For the second part with the current loop, you will need the Phyphox app on your smartphone. And this is a smartphone sensor app. We used it several times in the first semester labs. But if you didn't already download it, or if you didn't take those labs with us, just make sure that you download it now. It is available for most smartphones, but if between you and your lab partner only one of you is able to download it, then make sure that that person is the one who does the current loop experiment. For the magnetic field mapping, you'll need a blank sheet of white paper, some tape to tack down the corners, the compass from your lab kit, and the permanent magnet from your lab kit. Now you also need a pencil or some other writing utensil that doesn't have metal in the tip that could deflect the compass needle. So for example, if I move the magnet out of the way, I don't want to have that affect it, and then I try to use this pen, so I can place the pen right near the compass needle, and you'll see that it kind of deflects the compass needle, it attracts it to itself. So I won't be able to use something like that that has metal in the end of it. I'll have to use a wood pencil, or you could use a marker or something like that that doesn't have any metal in the end that will affect the compass needle. I should also mention that for this setup, you need to be sure there are no iron or steel objects close by that could affect the magnetic field you're mapping. And you also don't want any objects such as electronics or things that could generate their own magnetic field that would also interfere with it. So we'll start by taping down the corners of our paper. This is so that it won't change its orientation relative to Earth's magnetic field. We can't get rid of Earth's magnetic field, so we're going to have to just deal with it, and the way we do that is make sure that our paper doesn't change directions relative to it. Next, we'll need to place the magnet in the center of our paper, and you could put this either direction, I suppose. I'm going to put it like this, and then just tape it down to the paper so that it won't move. And we'll also want to just outline the magnet so that after we remove it, we'll still be able to see where it was. So for now, I'm really only able to mark the ends of it, but later on I can mark the rest of it after I remove it from the paper. Then we need to identify the poles of the magnet, so you can do this by getting the compass close and then seeing which way the needle points. So the red, or the north part of the compass needle, is always going to point away from the north pole of the magnet. So right now it's pointing to this left side, which means that this must be my south pole. So I could just label that as south, and we can check, see now the other side, the red is pointing away from that side, so this is my north pole. All that's left now is to map out the magnetic field lines, and we're going to do that with our compass. But we're only going to be looking at the direction of the compass needle. We're not going to look at the directions printed on the compass, north, south, east, west. We're only going to look at the direction that the compass needle is pointing, because that is a small test magnet. So if I just place this right here near the north end of the magnet, we can put a dot right here where the one end of the compass needle points, and then on the other side of the compass we'll put another dot where the other end of the compass needle points. So we've got two dots on here now. Then for the next point we can put the compass here so that this end of the compass needle points to the last dot that we put on there. And then we can put down another dot right here, again on the other side, and then do it again. So we put it right here, put another dot on the opposite side, and we just keep going around the magnet until we get back to the South Pole. So now we've got points mapped for one whole magnetic field line, and we can just connect them now with the pencil. Then we'll do the same thing with a new field line. So I'll just place it right here, put a point down for this side, put a point down for that side, line it up right there, put another point, line it up again, put another point, put another point here, and we just keep going until we either wrap back around or exit the page. And in this case, I have exited the page, so I'll just draw a line now that follows those points. So I've just continued this process of mapping the magnetic field lines using the compass and the pencil. And some of the field lines exit the page, some of them wrap back around, but the goal here is to just fill the page with as many field lines as you can, so that now I could approximate where any field lines would go in any of these gaps. So say this gap right here, I could approximate that the field line would go something like that. Or over here, I could approximate that it would go like that. So this just gives you a way to visualize the magnetic field for this permanent magnet. The last thing I need to do is add arrows indicating the direction of the magnetic field lines. So I said that they start on the North Pole and end on the South Pole. So we just need to add arrows indicating that. So I could put an arrow like that, an arrow like that, and like that. And then all of these are all going to point out from this side. So we'll just add arrows like that. And then over here, likewise, they're going to point in towards the South Pole. And that's it for this part. We've mapped out the magnetic field for the permanent magnet, and now I'm going to get started on the second part with the current loop. For the current loop experiment, we need to build a circuit that will generate the current for our coil of wire. The first thing we need to do is find our resistors. We're going to use three different resistors for this lab. We need an 82 ohm resistor, a 120 ohm resistor, and a 160 ohm resistor. I've explained in previous videos that we can identify the resistors from their color code. So the ones we're looking for today are gray, red, black, that's our 82 ohm resistor. Brown, red, brown is 120, and brown, blue, brown is 160. And each of these three have a gold tolerance band, that's plus or minus 5%. But if you happen to have resistors that are not 4 color codes, if they are 5 band color codes or some other number, then you'll need to look it up and see what the colors are for that number of bands. For this lab, we don't need to measure the resistors. We're only using them to control the current. So we don't really care what their exact value is. All we care about is the current that they produce according to Ohm's law. One thing we do need to measure is our battery voltage. And again, we don't really care what the exact value is, but we need to make sure that it's charged enough that it can supply the current we need for this experiment. We'll be needing a fairly high current, so we need to make sure that the battery can handle that load. As usual, let's make sure the probes are in the correct ports. So we want black in COM and red in V for volts. And then just turn the dial to 20 volts. And then let's check by placing the probes on the battery terminals. So I've got 9.62, 9.63, somewhere around there volts. That's plenty. If you find that it's below 8.5 volts, then you should probably replace the battery. And as I've mentioned in previous videos, whenever you measure the battery voltage, make sure that the dial is actually set to measure voltage. If you accidentally set it to current and you try to measure across the battery terminals, a lot of current will flow through the multimeter and blow the fuse. So just make sure that it's on voltage. Now it's time to build the circuit, and for this we need the multimeter to measure current. So let's start by turning the dial to 200 milliamps, and then let's check the probes, make sure they're in the correct ports. So again, black in COM, and then red in milliamps. So if your milliamp port is a different port, if it's not the same one as voltage, make sure that you plug this in to the correct port. I'm going to build the circuit real quick, and then I'll explain after I've done that. So this is the circuit, and it's actually fairly simple. We've got the battery here on the left, and then the red positive battery wire comes into the breadboard. Then from the same row I have a jumper wire going out to the side where I can connect this alligator clip. On the other end of that alligator clip wire, it connects to the coil. Then it goes around the coil and comes back out over here where I've got this yellow alligator clip wire connecting it from there over to the resistor. Right now I have 3 resistors in the breadboard, but we're only going to use one at a time. So we'll start with the 160 ohm, then we'll switch the cable over here to the 120, and then again to the 82 ohm resistor. So we'll start 160, then 120, and then 82 ohms. Back to the battery, we have the black negative wire coming into the breadboard. Then out of the same row, we have another jumper wire with this alligator clip wire attached. The other end of this wire is connected to the black probe from the multimeter, but the red probe is left disconnected for now. Next we need to measure the diameter of our coil, and we'll do that with the ruler. So if I just line it up here, it looks like about 11.9 centimeters, but we can check the other direction too to make sure that it's actually circular and not squished. So this direction it looks like 11.3 centimeters, so we know that it's squished in this direction. So I'm going to have to expand it a little bit, and then I'll tape it down to the table so that it stays in that configuration. Now the coil is taped down to the table, and that will keep it from changing shape during the experiment as well as keep it from moving. To get the radius of your coil, just divide the diameter by 2, and then you'll also need to convert it into units of meters. Last thing you need for the coil is the number of turns of wire, and this should be documented in the equipment list of your lab write-up. The one I have is a 50-turn coil. To record the magnetic field strength of the coil, we'll use the magnetometer tool in the Phyphox app on our smartphone. When you open the app, you should see the magnetometer, so select that, and then in the top right there's a menu, these 3 dots, so select that, and then it has switch to raw magnetometer. So you want to select that. So now if you were to go back again, it should say switch to calibrated magnetometer. We don't want the calibrated magnetometer, we need the raw magnetometer, so I'm just going to hit cancel now. Then on the main screen, we need the magnetometer Z-graph, so I'm going to tap that to full screen it. This should be the direction coming in and out of your phone. Now, before we can use the phone to collect data, we need to identify where in the phone the magnetometer sensor is. So it's going to be a sensor module somewhere within the phone, but we need to identify where that is. So the way we're going to do this is use the permanent bar magnet from the lab kit and the ruler, and we're going to tape the magnet to the ruler. So what I've done is taped the magnet at 12 centimeters, and this will keep it far enough away from the phone that it won't damage the electronics, but the magnetic field strength will still be strong enough that we can see it change as we move it around over the phone screen. So just hit start to record data on your phone, and then place the ruler with the magnet above the phone screen. So this keeps the distance from the phone screen the same, and then you can move it around and see how the magnetic field changes. So right here, yeah, see here it doesn't change very much from just the background field, but we can try finding other locations where it changes a lot more. So see, this is a lot more, and it looks like maybe here, yep, right around here is the maximum value. So the sensor is going to be right under where the ruler is right now. Now, just to clarify, I said you should look for the maximum value, but really you want to look for the most extreme value. Look for the place that changes the most relative to the background field when the magnet is away from the phone. And depending on whether you have the magnet oriented north-south or south-north, if you flip it upside down, then it will either increase or decrease as you move it closer to the sensor. The magnetometer in different phones can be in very different locations. Even in phones of the same brand, like I have an iPhone, another iPhone might have the sensor in a very different location. So you'll need to test this and see where it is in your phone. Now that we're done with the permanent magnet, you need to place it far away from the experiment setup because it's a fairly strong magnet and we don't want its magnetic field interfering with our measurements. Now that I've identified the sensor location in my phone, I can place the phone over the coil with the sensor directly in the center of the coil. Then for the rest of the experiment, leave the phone there. Don't move it again because we need the sensor location to stay constant relative to the coil. The rest of the experiment is fairly simple, but you do need to be careful and follow the instructions precisely. We're dealing with relatively high currents, so if you don't measure things properly, you could damage the multimeter. The process for this is we'll measure the background magnetic field, and that will be with zero current. Then we'll measure the current and magnetic field strength for each of the three resistors. First is the background magnetic field, and for this we'll need to leave the red probe disconnected, zero current flowing. Then I'll just hit start on my phone and let that go for a couple seconds. So that should be good, and then I'll touch the red probe to the opposite side of the 160 ohm resistor. Do not touch it to the same side as the alligator clip, because if you do, too much current will flow and it will blow out the fuse in the multimeter. So I'm just going to touch it right here. While that's going, hit hold. That saves the value, and then I can take it off. Do not leave it on the resistor too long or it will heat up and burn out the resistor. Then just record the current and then press hold again to go back to the live value. Then we need to switch the alligator clip to the next resistor. Again, place the probe there, press hold, let go, write down your value, press hold again, it goes back to the live value. Then we'll do the last one, switch it to the 82 ohm resistor, touch the probe to the opposite side, press hold, save the value, remove the probe. And that should be all we need, so I can go ahead and press pause there and write down this current on your paper. Now that we've collected all the data, I can remove my phone and use the Pick Data tool to go back and identify the magnetic field for each one of those measurements. So if we look at this graph, we have three spikes, one for each resistor. This is 160 ohms, 120 ohms, and 82 ohms. And then at the beginning and in between each of these is the background magnetic field. Now, it is possible that your graph will look like this, but flipped upside down, and that would be the case if you accidentally reversed your current and you had it flowing the opposite direction through the coil. Either way, though, it'll work the same. Just record the background magnetic field strength and the value for each one of these spikes, whether they're a spike up or a spike down. Also, your values will probably differ from what I have, and that's totally normal. Different sensors are going to have different raw values, but what really matters is the difference between values, and that should be relatively the same regardless of your phone and your geographic location. So just go to the Pick Data tool and then tap on the section that you need the measurement for. So this is my background magnetic field. It's negative 477.47 whatever microteslas. So that's the first value that I'll write down, and that will correspond to the zero current. Then I can do the 160 ohm resistor, and I've got negative 449.0268 microtesla. So that's the value I'll write down to go with the current that I had for the 160 ohm resistor. Then I can do the same thing for the other two and record their magnetic field strengths as well. Also, when you finish, don't forget to turn off the multimeter to save the battery. And that's it for the experiment. So just read your instructions carefully. They will have more information than what is shared in the video. And good luck on your experiment.